Hello, everyone. Welcome to the next part of this lecture. Um, we are going to very quickly do one kind of a interesting circuit problem, and the topic is on sequential switching, right? So we have talked about the natural responses of RL circuits, RL and RC circuits. We have talked about the step responses of RL and RC circuits, and in most of the circuits that we have solved and the derivations we did, we really looked at one switch, that is closing or opening at time t equals to 0. So interestingly, we're going to briefly talk about sequential switching, and we're going to learn that, for example, what is going to happen if you have multiple switches, for example, in the circuit, and how would that changes stuff. So let's get started to this. Here's really the summary of whatever we talked about, right? um, and I hope that this should be very easy to remember. Um, in order to solve for example, for the natural responses, all you need to remember is that you need to solve for I naught and V naught for t is less than 0, right? You need to find the time constants L over R and RC by finding the equivalent resistances and the conductor and the capacitor values. Of course, find the tau for greater or equals to 0, right? And then putting the values back into this inductor current and capacitor voltages. And when it comes down to the step response, um, I guess there's one equation missing, step response of an RL circuit. Uh, right, essentially you have to find three things. You have to find the initial voltage of a capacitor, the final voltage of a capacitor, and the time constant tau. And similarly for the step response of a RL circuit, you have to find the initial current of the inductor, the final current of the inductor, and the time constant. Okay, anyhow, let's come back to, okay, here's the equation. The final current, the initial current, and the time constant. Okay, so let's come back to today's topic, that is sequential switching. So what is sequential switching? As I was saying, sorry, my iPad is slightly, okay, sequential switching. So the idea is that, let's assume that, sorry, if you have multiple switches in the circuit and that are going on and off at different times, what is going to happen? This is called sequential switching, right? So it could be, for example, two position switches in which there is one switch at position 1 at T1, that switch can become at position 2 at T2, or you could have multiple switches that may be opening or closing. Anyways, right, irrespective of how many switches you have, um, the concepts will remain the same that we discussed in the past. All you have to do is to find the inductor current, capacitor voltages, and the rest of the associated values. And while understanding a fundamental concept that inductor currents and the capacitor voltages does not change instantaneously. This is pretty much it. We are going to do this example problem, and this is a very interesting example problem. It may take like some time to solve this, but this is going to give you kind of another very good exercise of how the entire thing is happening. Okay, so let's see. Okay, here's an example problem. In the circuit, both switches were closed for a long time, right? So both switches 1 and 2 were closed for a long time. So this means that your 60 volts voltage source, DC independent voltage source, was providing energy in this kind of a resistive network for a very long time to the inductor till it reaches a steady state value. And practically we know that once it reaches a steady state value, it's going to become a short circuit. Anyhow, at time t equals to 0, the switch 1 gets opened, and after 35 milliseconds, switch 2 gets opened. And the question asks us to find the value of IL, the inductor current here, right? This is IL. Um, After the switching, after the first switch gets opened, right? So finding the inductor current for 0 to 35 millisecond, and then finding the inductor current for 35 millisecond onwards after the switching event 2, right? So this is after switch 1, this is after switch 2. And then we have to find some of the overall energy that gets dissipated in a 18 ohms resistor, 3 ohms resistor, and a 6 ohms resistor. during the switching events as well. So kind of a very interesting problem. Let's get started. Okay, so let's start with the problem number one. Solution for the A. Solution is I'm interested in find the inductor current in between 0 to 35 millisecond. Whenever I have to find an inductor current, right? So by the way, right, at time t equals to 0, the switch 1 gets opened, which practically means that we are looking at the natural response of a circuit where the inductor gets fully energized and then we kick the excitation source out. So the natural response current inductor current equation is I naught e to the power minus t over tau. And we also know that how to solve this, essentially finding the initial conditions and the time constant. So let's get started with this thing. The very first thing I need to do in order to find this IL, right? Practically, I'm going to realize that IL is going to come out to be e to the power minus t over tau. So in order to find this out, I am going to do the very first thing, I'm going to find the value of I naught. In order to find the value of I naught, I need to draw a circuit at t is less than 0. For t is less than 0, right? Inductor is in steady state and short circuit. Okay, so let me draw the circuit, how the circuit is going to look like. 60 volts, 4 ohms, 12 ohms, 6 ohms, 3 ohms. Here is that inductor and it has been shorted. Right, so this is 3 ohms, this is 6 ohms, this is 12 ohms, this is 4 ohms, and this is 60 volts, right? Okay, so this means that if this inductor is shorted, then that the last resistance shouldn't be over here, because of course that was shorted out by the inductor behaving as a short circuit. So that is why this is how the circuit is going to look like at t is less than 0. Okay, this is interesting. All I need to do is to find the value of the current that is flowing over here, IL at 0 negative. Okay, so how I can find it? Practically, let me do this by solving the circuit and finding the value of the voltage that is appearing over here. I am interested in finding the voltage that is going to appear over here, and then I can just use Ohm's laws to solve this. Let me start by finding the equivalent resistance, right? So I know that 3 ohms and 6 ohms are in parallel, and then again they are in parallel with 12 ohms. So let me find some sort of RA, equivalent resistance, which is going to be first 3 ohms and 6 ohms is going to be parallel, and that is going to be parallel with 12 ohms. So 3 times 6 is 18 divided by 9 in parallel with 12, 2 in parallel with 12. So RA comes out to be, so this is going to come out to be 12 times 2 is 24 divided by 14. So the value of the RA is going to come out to be 1.7143 ohms, right? So practically the circuit that I'm looking at now is 60 volts, 4 ohms, 1.7143 ohms, this. And I want to find the value, so this was my RA, right? I can find the value of the VA over here. So in order to find the value of the VA, I can apply a voltage divider rule. Again, simple. Voltage divider rules is 60 volts multiplied by the resistor across which I'm interested in finding the voltage, 1.7143, divided by the summation of both of them, 4 plus 1, 5, 7143. If I were to solve this VA, I am going to get the answer to be 18 volts. Right? So I can see that the voltage across over here is going to come out to be 18 volts, right? So the voltage here is 18 volts, the voltage here is 18 volts. So my current IL that is going to flow at 0 negative, at t is less than 0, is gonna come out to be 18 volts divided by 3 ohms, 6 amperes, right? So my I naught is 6 amperes. Okay, so this is nice. Let's do the second part now. So I know that in order to find the inductor current in a particular condition in a natural response, I need to find the time constant. So time constant I need to find, and I usually find the time constant after the switching event. So we have to redraw the circuit now. Redraw circuit. So let's redraw the circuit after the switching event. If this switch gets opened, if the one switch gets opened, right? So we are looking at this part of the circuit now. Right? So we have 6 ohms resistor, 3 ohms resistor, we have an inductor, and then we have another resistor. So 18 ohms inductor L, 3 ohms resistor, 6 ohms resistor. I can easily see that now. Tau we know that is equals to L over R. The value of the L is 150 millihenry. 150 millihenry. Okay, so let's find R equivalent here, right? So R equivalent is, I can easily see that 6 and 3 on the series, which is in parallel with 18K. So 6 in parallel with 3 plus 18. So this comes out to be 6 times 3 is 18 divided by 9. Oh, sorry. They were in series and the other one is in parallel. 6 plus 3, 6 plus 3 in parallel with 18, like this. Yeah. So 6 plus 3 is 9 in parallel with 18. So this is going to come out to be 9 times 18 divided by 27. Should come out to be 6 ohms. Okay, so once we get that, I can replace this value over here, or let me rewrite this. L over R equivalent. L is 0.15 Henry. It was 150 millihenries divided by 6 ohms. It is going to come out to be 25 milliseconds. Okay, nice. I ended up finding the value of both I naught and the value of tau. All I need to do is to write down the equation now, which is I naught e raised to power minus t over tau. So I got I naught is 6 e raised to power minus t over 25 millisecond. And of course I can do 1 over 25 milli comes out to be 1 over 0.025 comes out to be 40, right? So I can rewrite this thing as IL of t 6 e raised to power minus 40t amperes. And again, this is for 0 to 35 millisecond. Okay. So I ended up doing the first part of the circuit, right? So we ended up finding the value of the inductor current for 0 to 35 millisecond. Now let's solve this entire thing again for the second part where I'm interested in finding the inductor current for 35 millisecond, right? Now I want to do a B part here where I am interested in finding the inductor current again, but for t greater or equals to 35 millisecond. Right, so same drill. The very first thing I need to find is initial current. Initial current for t less than 35 millisecond. I know this is the value of the current that was less than 35 milliseconds. I'm just going to use this equation directly, right? So I'm going to use IL exactly at 35 millisecond equals 6 e raised to power minus 40 times t 35 milli, right? So if I were to solve this, I at t is equal to again 35 millisecond. You can also write it like this. Right? If you were to solve this, it is going to come out to be 1.48 amperes, right? So okay, so IL comes out to be 1.48 amperes. This is the initial condition of the second switching event, right? So this is okay. Let me sorry. Okay, sorry. Let me. Oh my god, it got stuck. Let me do this thing again. Again, this is the initial condition of the second switching event. This was the initial current that was flowing, 1.48 amperes. Right? So for, and this is, you can call it I naught 1.4 ampere, 48 amperes for switch 2, or for the second switching event for this time window. Okay, so we ended up finding that. Now we have to find the second part of it, which is again have to find the time constant again, right? And again, this needs to be found for a new circuit, which is greater or equals to 0 after the second switching event. So once this switch 2 gets opened, essentially I also kick out the 18 ohms resistor, and my circuit will remain 6 ohms, 3 ohms, and 150 millihenry resistor. So my circuit will be reduced even a lot more, and I will be left with 6 ohms, 3 ohms, 150 millihenry inductor. So this is my practically circuit is left with. So I can easily do this thing L over R. Equivalent L is 0.15 Henry divided by 9. Time constant comes out to be 16.67 millisecond. Okay. So I ended up finding both of these things. Now let's just put them both in our equation that we have, right? And again, our equation of the inductor current was I naught e raised to power minus t over RC. I know the value of RC. Okay, so the one interesting thing before I solve this. This equation was derived, if you remember, by solving an integral for 0 to t. And we said that the switching was happening at time t equals to 0. This equation and all the associated equations will change if I will change the time of my switching, right? If I will call this time t equals to 0 as t naught over t, all of my equations will change, including this one. For example, this equation will become IL of t equals I naught e raised to power minus t naught over RC, right? And again, you can go back and see that this is the subtraction factor that was initially being neglected because we were assuming t naught to be equals to 0. That was the switching time. So essentially, I have to put now both of these values in this new equation of the inductor current, where I have t minus t naught. Okay, so IL of t is I naught e raised to power minus t naught divided by RC. I naught is 1.48 amperes, right? E raised to power t minus t naught. T minus t naught is again 35 millisecond, the time of the switching event, right? So over here, t naught is 35 millisecond switching event, right? So I can do 0.035 in terms of seconds, and I can divide this by the value of the time constant, which is 16.67 milliseconds. In seconds, 0.0167. So once I do that, I can further solve it and reduce this equation to 1.48 e raised to power minus 60 times t minus 0.035 amperes. Again, and this is for t greater or equals to 35 milliseconds. So here's the value of the inductor current after 35 millisecond or after the second switching event. Again, right, so this is very nice. The only interesting thing or different thing that happened over here is t minus t naught. It's very simple because all the integrations, all the derivation that we have solved for was for the switching event that was happening at t equals to 0. However, if it doesn't happen for t equals to 0, in the e exponent it becomes t minus t naught, which you can easily go back and look at any of the derivations and assume that the lower limit of integration when we were integrating with respect to time should come out to be t naught, right? If we were to put t naught, it's going to come out to be e raised to power t minus t naught. Okay, so this is nice. Let's go back to our third part. In the third part now, I am interested in finding the energy dissipated. Okay, the percentage of the energy stored in 150 milliamps of Henry inductor and is dissipated in the 18 ohms resistor. Okay, so here's the deal. Before any of the switching events happen, your voltage source 60 volts was providing the energy to the inductor, right? And it ends up providing the maximum amount of the energy or the total amount of the energy in the inductor before any switching events happen. So that is the total amount of the energy stored in the 150 milliohms inductor, right? At t less than 0. And then as soon as the first switching event happen, right, the first switch opens at t equals to 0, the excitation source gets out and the energy starts to get dissipated. And we can see that this 18 ohms resistor is only present after the switching event 1 while the switch 2 is closed. As soon as the switch 2 will be open as well, 18 ohms resistor will be kicked out. So in terms of the how much of the energy gets dissipated in 18 ohms resistor, we are interested in finding out or integrating the amount of the energy from the switching event 1 before the switching event 2. Okay, so let's end up solving this thing. So before we solve this C part of it, let's first find out how much is the total energy that is stored in the inductor, right? Total energy stored in 150 millihenry inductor, which we know that, right? So half L I naught square. And this I naught is, we already figured it out, right? This is the first I naught, which was 6 amperes. So half times 0.15 times 6 square, you would get approximately equals to 2700 millijoules. Okay, so this is the amount of the total energy that was stored in the 150 millihenry inductor. Now the first switching event happened, the excitation, the voltage source gets kicked out the 60 volts, right? And the energy will start to get dissipated, the power and corresponding the energy in the resistors. So let's look at that now. Okay, again, let me see. The voltage across the 18 ohms resistor over here is, right? So voltage across this resistor, 18 ohms resistor, should be equals to the voltage across the inductor, right? VL. So I can easily find, let's find now, the power dissipated in 18 ohms resistor. Why I'm finding the power, then I can easily integrate the power to find the energy, right? So the power dissipated in the 18 ohms resistor, since the voltage across the resistor is the same as the inductor, right? So VL should be equals to L di by dt. So L is, and this should be equals to V 18 ohms as well, right? So L is 0.15 millihenry. So, and the derivative di by dt, let me just do this thing. And what is the equation? Equation was here. This was the first part of the equation, 0 to 35 millisecond, right? 6 e raised to power minus 40t. 6 e raised to power minus 40t. Okay, so let's solve this thing. 0.15 times 6 times minus 40 e raised to power minus 40t. So if you were to solve all of that, this should come out to be V 18 ohms should come out to be minus 36 e raised to power minus 40t volts. So this is a voltage across 18 ohms resistor. So once you find out that, right, you can easily find the power across the 18 ohms resistor should be V squared over R. V squared is minus 36 e raised to power minus 40t square divided by R is 18. Uh, right? So essentially minus 36 square e raised to power minus 80t divided by 18. And this comes out to be power dissipated in 18 ohms resistor should be 72 e raised to power minus 80t watts. This is the power that gets dissipated in 18 ohms resistor. So once you find it out, now you have to find the energy dissipated there, right? Energy dissipated in 18 ohms resistor. And we have done similar problems in the past along with some of the derivations as well. Essentially, when we are trying to find out the energy, all we do is we kind of integrate, right? And again, we know that the energy is only dissipated in the resistor, 18 ohms resistor, in between switching 1 and 2 events, because after switching 2 events, when the switch 2 gets opened, 18 ohms resistor gets kicked out as well out of the circuit, right? So my limits of integration is going to be practically 0 to 0.35 seconds. Or 0 to 35 milliseconds, right? Okay, so I know that this should be power times dt, 72 e raised to power minus 80t dt, right? And if I were to solve this again, I can show you this identity again. So for example, if you were to do a to b e raised to power minus 10t dt, this should be equals to 1 over 10 e raised to power minus 10a minus e raised to power minus 10b, right? So you can apply this identity over here. So the energy that gets dissipated over here should be equals to 72 times minus 80, and again I can apply e raised to power minus 80, 0 to 0.035. And if you were to solve this, 0.91 minus e raised to power minus 2.8. Okay, so if you were to solve this, it is going to come out to be 845.27 millijoules. In between switching 1 and 2 events, the amount of the energy that gets dissipated in the 18 ohms resistor should be 845.27 millijoules, right? And again, after that, it will be kicked out. And before that, the energy was being stored in the inductor. So the percentage of energy that gets dissipated comes out to be, right, 845.27 divided by the total energy, 2700 times 100. Right, so it should be 31.31%. So the total amount of energy that gets dissipated in the 18 ohms resistor was 31%. Let's very quickly solve for the D part now, right? So the D part is I have to repeat the whole thing for a 3 ohms resistor and for a 6 ohms resistor in the next part. I don't want to go back and forth again and again, but the point that I want to make it over here is for a 3 ohms resistor, we have to solve the entire thing twice, right? The entire energy dissipation problem. One, if you look at, so again, before t is less than 0, before the switching events, energy was being stored in the inductor, 2700 millijoules, and then it starts to get dissipated. After the switching event 1 t equals to 1, when this portion of the circuit got out, right, the energy was being dissipated in 3 ohms resistor, and the circuit had a 18 ohms resistor. After the switch 2 opens, 18 ohms resistor also got out, and your circuit does not have a 18 ohms resistor. Again, the 3 ohms resistor was there, so energy was being dissipated in a 3 ohms resistor. So a different amount of energy got dissipated in a 3 ohms resistor and a 6 ohms resistor when there was a first switching event and after the second switching event. So we have to find that separate energies separately and then integrate all of that together, right? So that is one thing. Okay, why don't we solve it, right? So okay, so I wanna do the C part here, D part here, which is I have to energy dissipated in 3 ohms resistor. Okay, so in order to solve that problem, Uh, um, let me go back, right? So one, by the way, the initial amount of the energy that is stored should remain the same, 2700 millijoules, right? So let's solve for the D part, in which we are interested in a 3 ohms resistor. And I'm going to solve it for like two different parts, 0 to 35 milliseconds, and then beyond greater than 35 milliseconds. So let's first do in between 0 to 35 millisecond. In between that time, the voltage, yeah, it shouldn't be exactly zero because this only makes sense at zero positive. So that is why there is no equal sign here. Okay. Anyhow, so if I go back to the circuit, show you maybe again, in a 3 ohms resistor, right? What we are going to do is how we are going to solve the value, the amount of the energy that gets dissipated in a 3 ohms resistor. What I'm going to practically do is I'm going to find the value of the VL, right? Or use the value of the VL and apply the voltage divider rule, right? If this is the voltage VL that is appearing at this node A, for example, then after switching event 1 and practically at 2 as well, I can apply that a voltage divider rule to find the voltage across the 3 ohms resistor. Okay, so at 0 positive, we know that in between 0 to 35 millisecond, the voltage across the inductor comes out to be 0.15 di by dt, and di by dt was equals to 0.15 d by dt e raised to 6 times e raised to power minus 40t, right? Minus 40t, and we know that this was equals to minus, we already solved this thing, minus 36 e raised to power minus 40t volts, right? I have derived this thing. Where is it? Okay, this is over. Sorry. Okay, so this is over here. Okay, this is over here. No, this is the voltage across 618 ohms resistor. But practically the equation was the same, because this was the inductor voltage. Okay, and so let me clarify here, right? So why the voltage, right? Essentially what I was showing you is that the voltage over here across the inductor 150 millihenry is the same as the 18 ohms. So that is why that look, right? So that is why this came out to be this voltage. It was exactly equals to VL. So again, VL comes out to be minus 36 e raised to power minus 40t. I can easily do the voltage across the 3 ohms resistor by applying a voltage divider rule. So it should be this VL times 3 divided by 3 plus 6. Again, those two resistances. So 3 over 9 times minus 36 e raised to power minus 40t. So voltage at the 3 ohms comes out to be minus 12 e raised to power minus 40t, right? And this is volts. Okay, so once I find the value of the voltage, essentially I can find the power and the energy as well. Energy, right? So whenever we do energy, it is practically over here 0 to 0.035 in between the first switching event. Power V squared divided by R times dt. So I can write this at 0 0.035 minus 12 e raised to power minus 40t square divided by 3 times dt. And again, I can solve this by 3 ohms, 0.035 minus 12 square 144 e raised to power minus 80t divided by 3 times dt. And again, you can use this identity here again to solve for this equation. And the amount of the energy for a 3 ohms resistor in the first switching event is kind of come out to be 563.51 millijoules. Okay, so this is the amount of the energy that comes out to be. And again, this is in between 35 millisecond. Now the problem is my 3 ohms resistor stays after the second switching event, right? So after second switching event, which is practically t is greater than 35 millisecond. So I have to redo the whole thing again. Um, and again, so for example, in order to do that, let me show you the circuit after the second switching event. Right, so after the second switching event, when the second switch will be opened, my circuit is only going to have a 6 ohms resistor, 3 ohms resistor, and an inductor. Right, so this is only going to have 6 ohms, 3 ohms, and an inductor. Right, 150 millihenry, 6 ohms, and 3 ohms. So essentially, I'm going to use the value of the inductor current and use that to find the power dissipation over here, right? So what is the value of the inductor current? IL of t for t is greater than 35 millisecond, right? I ended up calculating right over here, 1.48 e raised to power minus 60 minus 60 t minus 0.035 square minus point. Okay, right, so I'm going to use this one. Okay, so let's again, your work done at 3 ohms should be equals to, again, this is from 0.035 to infinite, and I'm going to do I square times r times dt, 0.035 times infinity. R is 3 ohms, and I can use the equation I, 1.48 e raised to power minus 60t, 1.48 e raised to power minus 60t minus 0.035. T minus 60, t minus 0.035. Okay, so if you were to solve this again using this identity, right, rest of it is just constant, right? All of this is just constant, and then you can easily solve this thing by that. You're gonna get, the value that you're gonna get is 54.73 millijoules. So the total energy that got dissipated was both the amount of the energies. So for example, this one in between 0 to 35 millisecond and greater than 35 millisecond as well. So you get 563.51 plus 54.73. The total comes out to be 618.24 millijoules. So what's the percentage of the energy dissipated? The percentage of the energy dissipated was your 618.24 millijoules divided by 2700 millijoules. Again, that was the total amount of the energy that was stored. In 3 ohms resistor, 22.9% of the energy got dissipated. And the last part of the problem again is repeating the entire analysis for the 3 ohms resistor, but for a 6 ohms over here. If you look at the 6 ohms, I'm not going to do the whole thing because I can use a trick, if you call it. If you look at the 3 ohms resistor and the 6 ohms resistor, both of those resistors after the switching events were in series, right? After the first switching event, this entire thing got out, right? And you were left with the right-hand side where 3 ohms and 6 ohms were in series. So and in both 3 ohms resistance and 6 ohms resistance, some of the energy got dissipated in between 1 and 2 switching events, and then another different amount of the energy got dissipated after the second switching event just because of the presence of a 18 ohms resistor. Okay. During the first switching event. So since 3 ohms and 6 ohms are in series, so whatever the amount of the energy that got dissipated in 3 ohms, 6 ohms should have exactly the double amount. And we will verify that, right? So 6 ohm resistor is in series with 3 ohms resistor after t is greater or equals to 0. All the way after the second switching event too, they always remain in series. So energy dissipated in 6 ohms should be double than 3 ohms, right? So we can do the amount of the energy dissipated in 6 ohm 2 times 618.24 millijoules. This should come out to be 1236.48 millijoules. Now let's verify whether this makes sense or not. Again, let me show you the circuit before doing this kind of a verification step. If I look at the switching events, right, after time t equals to 0, the energy source gets kicked out, the excitation source, voltage source gets kicked out, along with the 4 ohms resistor and a 12 ohm resistor. There are only 3 resistors that remains in the circuit after time t equals to 0. 3 ohms, 6 ohms, that remain there for both switching events. After switching event 1, after 2 it remains there. And 18 ohms resistor is only present in the first switching event and then also kicked out after the T second switch gets opened. So the total amount of the energy that was stored was 2700 millijoules, right? So ideally, that amount of the energy should eventually get dissipated in all the 3 resistors because there was no other presence of an excitation source to provide energy to an inductor. So in order to make sense that our calculations are correct, we can just sum up all the dissipations. Dissipations across 8 ohms, dissipation across 3 ohms, dissipation across 6 ohms should be equal to the total inductor energy, right? So let's verify that. So that should be 8 ohms was 1236.48, 3 ohms was 618.24, 6 ohms was 1236.48, right? If you were to millijoules, if you were to sum them up, it should come out to be approximately, maybe with a one significant figure difference, 2700 millijoules. So this provides us a verification that our calculations are correct, right? Or law of conservation of energy is still there. Okay, so this is pretty much it. Again, some of the take-home message before I end this lecture is don't be afraid of the switching events. All you need to do is to remember these equations, literally your natural responses and the step responses, and there's nothing else, and some of the basic concepts that the inductive current and the capacitive voltages does not change instantaneously. And you need to be a little smart in solving these circuits. You should know that after a switching events, what is the circuit that is remaining, how to find equivalent resistances, to find the time constant, understanding that, again, this point, right, this is going to be super helpful while doing all of this initial voltages calculation in RC circuits and initial current calculations in RL circuits, right, because of the open circuit and the short circuits equivalencies that we usually establish, right? And then it all comes down to solving your basic circuit, right? Things are in parallel, series. You apply Kirchhoff's laws, Ohm's law, you apply voltage divider, current divider rules, and energy calculations, right? So hopefully this should be useful. Again, if there's any confusion in any of this example, this is a kind of a very long example where we have to spend time to solve a lot of things. So you're more than welcome to circle back with me on this. Okay, sounds good. Thank you so much. Have a great rest of the day. Thanks. Bye.